Dear viewers, thank you for your interest in our concepts for repurposing gas and coal power plants. I am Miroslav, Deputy Managing Director of Solenco, and I am pleased to present to you the part 5 of Solenco's concepts. In this part, we will talk about hydrogen for power generation, in particular retrofit of the existing gas turbine combined cycle. This concept introduced the idea how smoothly to execute the transition to hydrogen productions for different sectors, and how effectively can be utilized the surplus energy from renewables, and simultaneously how can be reduced greenhouse gas emissions at existing plants. Let's get started. Before we start talking about the concept, please allow me to say a few words about the background that gives us the confidence to prepare such a concept for the retrofitting. Solenco team is a pioneer in hybridization of technologies. Already in the 19th of the last century, George Brackman, the founder and the managing director of Solenco, provided by his thermodynamic design and calculation the soundness of the ISCC technology, and thereby convinced the World Bank to sponsor 4 initial ISCC projects with an amount of $50 million each. After this World Bank's support, other ISCC projects have been developed and built. Solenco team was involved in 3 of these projects that you can see in the presented table. 2 of them, one in Egypt and the other one in Morocco, were financed from the already mentioned World Bank grant. If you are interested in these ISCC projects, you can find further information about them at the YouTube Solenco channel, Solenco website, or you can search for ISCC projects in internet. George Brackman's innovation and excellence in engineering resulted in his company receiving in 2011 the prestigious Frost & Sullivan Green Excellence in Technology Innovation Award. All up, we have a successful track record in turning strategies into real projects and implementing emerging technologies in the global scale. Let me introduce to you the ISCC project in a nutshell. We will start with the gas turbine that operates on the natural gas, or that cannot reliably operate on a variety of gases and liquid fuels, provide energy security in the event of fuel supply disruption. Then we will follow the exhausted gases that led us into the heat recovery steam generator, which is one of the major equipment in the gas combined cycle power plants. The HRSG is a kind of heat exchanger in which the heat from the exhausted gases recovers to an extreme degree that we can derive from the difference in the inlet and outlet temperature of the exhausted gases. The heat is led into the form of superheated steam to the steam turbine. The condenser and feeding water system close the water steam cycle. Another important part of the plant is the cooling system. And as we can see in the simplified schema, the power evacuation into the grid is from both generators, which allows a great flexibility in operation as an open cycle and as a combined cycle. The concept is well known, and we have thousands of installed such plants around the world. As it is already shown in the HRSG, there is a heat exchanger which is accommodating the solar heat and convert the gas turbine combined cycle into the integrated solar combined cycle. Solenco concepts for the ISCC is using parabolic trough solar field with thermal energy storage. In the ISCC configuration, the high temperature heat transfer fluid generates slightly superheated steam that is a parallel water steam loop to the one of the HRSG. Such configuration of ISCC ensures that the efficiency of the ISCC is much higher than for the standalone solar plant, and improve the efficiency of the combined cycle plant, as well as it reduces the CO2 emissions proportionally to the solar share. This type of power plant is considered particularly attractive in the region with the high DNI and low incident angle, such as North Africa, but there were the abundant sunlight and an availability of natural gas. The reason of presenting the ISCC technology in this part 5 is to ensure the viewers that Solinka team is a pioneer in the hybridization and has a practical experience in designing both the gas turbine combined cycle and the high-efficiency solar power plants. This statement is proven by many years of successful commercial operation of the already mentioned ISCC plants. As presented in the part 2, we in our concepts are focusing on production of green hydrogen from the owner's renewable sources and from the green surplus energy that is available in the grid. A renewed interest in the polymer electrolyte membrane electrolysis as a valuable solution for hydrogen production stimulates electrolyzer development for the future application in hydrogen energy and technology. Despite the fact that we do not need pure hydrogen for this concept of the H2-O2 steam generator, nevertheless we consider usage of the produced hydrogen for other sectors as presented in the part 4. Thus we are considering the polymer electrolyte membrane electrolysis as a basis. The produced hydrogen is then compressed. The design pressure depends on many factors, in particular on the highest requested pressure by a sector of the distribution. Considering the large central hydrogen production facility, that determines the design of the multi-stage compression, wherein cooling the hydrogen during its compression will reduce the cost of compression work and open an option to utilize the waste heat for heating or cooling purposes. The compressed hydrogen is then stored in the hydrogen storage that we consider as an energy storage, from where it is ready for further distribution into the sectors as we have presented in the part 4. Let me describe the selected GTCC plant configuration in a nutshell. 2 gas turbines, heat recovery steam generator, smoke gas channels, smokestack. From that, the greenhouse gases are emitted. Here we have the water steam cycle with the steam turbine and its generator, the cooling system, and now we can add the gas turbine generators to see all 3 power sources supplying power into the grid. When the GTCC is operated at 100% of the design power, I mean when both gas turbines are operated at 100%, then the steam turbine is operated in the full load, which does not allow to accommodate any steam coming from H2-O2 steam generator. I would like to point out that we are presenting the concept for the retrofitting the existing plant. Of course, if a new plant with this configuration would be designed, then certainly the steam turbine would accommodate the full load from the HRSG and the full load from the H2-O2 steam generator. So, in the existing GTCC, the operators must operate at least one of the gas turbine in the part load in order to create a sufficient capacity at the steam turbine that allows to accommodate the load from the H2-O2 steam generator. Because majority of the already installed GTCC are operated in part loads and serving for power generation during shoulder, peak and super peak production times, it is not a problem to adjust the operations manual for operating the plant with utilizing the green energy via H2-O2 steam generator. That mode does not have any negative impact on the plant's economy. Please let me draw your attention to the biggest advantage of this concept, that is the significant reduction of the CO2 and other greenhouse gas emissions. This concept introduced the production of the superheated steam in the H2-O2 steam generator that occurs in the second, and the combination with the flexibility of the gas turbine operation allow the operator a great flexibility in the grid stabilization, and furthermore it opens a great potential for a digitalization not only with the plant's operation but also in the grid operation. For example, one of the operational modes is the one when one gas turbine is operated at 100% and the other one stands by. The steam load from the HRSG on the steam turbine is stable, and the load from H2-O2 steam generator ensures the dispatchability as per actual grid demand. It is definitely clear that this is technically limited by the capacity of the steam turbine. In case that stored green energy cannot satisfy the grid demand, then standby gas turbine is taking over the grid stabilization. This operational mode significantly reduces the CO2 emission and other greenhouse gas emissions. However, the gas turbine remains producing greenhouse gas emissions. Consequently, the plant is not climate neutral, and most probably the GTCC will not be allowed to be operated after 2050. Nevertheless, it is 29 years from now, and therefore the concept is worth it to be considered, especially for the transition period to the hydrogen as energy carrier. Let me sum up this presentation. This concept offers the technical and economical solution for repurposing the existing gas turbine combined cycle and could be also applied for coal power plants. The concept ensures the reduction of greenhouse gases, utilization of surplus energy, stabilization of the grids, and finally it opens a perspective for a development of hydrogen as energy carrier across many sectors. If you are interested in further our concepts, you are welcome to visit us at YouTube, LinkedIn, and Solinka website. If you are interested in our services, please contact us for initiating further steps. Thank you for watching.